Okay, and then I think I'll go ahead and I think I'll do the speaker view. So it, let's see, I don't know why it's doing Jake. Okay, there we go. All right, well, whatever. Anyway, okay, so I will go ahead and we'll just dive right in. So here we go. I'm going to share my screen and do the slides. So introduction of Verilog. So this is the lab schedule, by the way. So Monday, Tuesday, Wednesday, 2 to 4:50, or maybe it's 2 to 4:45, I forget. And Wednesday, 2 to 4:45. And then Tuesday, it's 11:30 to 2:15. There's about room for 30 in each lab. You can go to any other labs you want. You can swap with a student to make it sort of legit. You can jam in, but you might not have a computer. But you're welcome to see. Although we do want to not overcrowd just due to COVID, so we'll look at that as well. And then there are, I forget how many labs, but we will have at least one session that's a makeup lab session near the end. You can only miss one lab. Otherwise, you really haven't qualified to get a grade for the course. So I usually give an incomplete for that. I might just, cause it to affect your grade. I don't know. I've had mixed results with people making up their incompletes, I have to say. Okay. So all the lab assignments are in the lab folder in Blackboard. You can certainly do your work at home, but I do want you to demo it to the TA in person if possible. If you really have an extreme situation, then fine, you can do a video and send that video to the TA. But I really would like to see everybody in lab most of the time because I think you'll learn more that way. But feel free to do your lab. If you want, you can do all your work at home. You can bring it in. If you didn't have any problem, just demo it, and then you can. But usually at the beginning of lab, I'll do a little quick 5-minute discussion about the lab and kind of what I want you to learn from it. So I kind of like you to be there for that. Anyway, so try and come to lab if you can. And we will be doing the in-person labs for the first 3 weeks, and then we'll continue after that. But the lectures, we'll do those online for 3 weeks, and hopefully we'll be in person. And hopefully in lab, you can not just do what's assigned, but you can play around a little bit, make some changes to the actual assignment, and try and just get a little more experience with Vivado and Verilog. Okay, so all integrated circuits in the United States and most FPGAs are programmed with Verilog. But if not Verilog, then VHDL or System Verilog or System C. But essentially, one of these hardware description languages is used for everything. And so this is how all digital devices get done these days. The only other way we do anything is you're doing an embedded project with an embedded microprocessor, and you're writing the microprocessor code. But more and more, we're using devices that most of our digital devices have an FPGA and a microprocessor. Usually, in that case, often the microprocessor will be built into the FPGA, but that might not be the case. It might be a standalone chip. But in any event, combining a microprocessor and an FPGA this is pretty much how things are going to go. So I really, this is important stuff. You're probably going to be using and writing a lot of Verilog code over your career, or System C code, or whatever the equivalent HDL language is. System C and Verilog are very close, so it shouldn't be a big step. The concepts and principles, though, are very important to grasp, and that's definitely what you're going to learn in this course. And the idea is that when you write an HDL script or program, it's not the same as a computer program, and you have to think differently. So, and that's pretty much what you have to learn in digital systems design. Okay. All right. Well, so here's how things get fabricated. You basically create the design on, using English language statements, a hardware description language, and a big integrated development environment. And then once you get that all entered and verified and debugged, then you basically hit a button, the synthesizer grinds away, and it cranks out all of the photomasks that are used to actually make the chip, because we're still using photolithography for chip production. This is actually hard to even comprehend how this works, because the wavelength, we're making chips that are 10 nanometers now in feature size, but we're using wavelengths of light that are they're using the the shortest wavelength light, non-visible light they can get, but still those wavelengths are hundreds of nanometers. And so how a light with a wavelength of several hundred nanometers can produce a 10 nanometer feature on a photomask is beyond me, but that's what happens. We start with sand, very pure, highly purified. We melt it down so it's liquefied, very hot, and then we seed a crystal, and then we grow the crystal out of the sand. And those crystals are huge. They weigh, like 100 pounds or maybe more. They're very heavy. It looks like glass essentially, and they're what, about 7, 8, 12 inches in size. They're pretty good size, and it's pretty standard. And then they take this crystal that's grown and they saw it up into these thin wafers, and then they deposit some films on top of the wafers, and then basically then this goes to it gets covered with photoresist. The masks are used, and the way the masks are done, they're usually multiple there are multiple patterns on this thing. The photomask just has the one circuit, and then so it's moved around on this die to create the pattern in a whole bunch of different places. There could easily be several hundred chips on a die on a wafer. So, and they're all created at the same time, which is partly how they get reduce the cost a little bit. And then they go through step after step of etching, washing off the non-exposed photoresist, and then etching it, then depositing it, doping it with to make it a P area or an N area, to creating the channels or whatever. And typically most of the transistors on this wafer are identical. There might be a few that are different, that are line drivers and things like that, but they try and use regularity as a feature to get this to work. And then once it's gone through however many steps and different photomasks are required to make the chip, then it's done. It's tested. It's sawed into single individual chips. The individual chips then have leads bonded onto them with bonding wires, and then they're connected to these days not pins typically, but pads, so that they can be surface mounted. We still make some chips with pins, but the number of chips that have pins is going down, and almost all of them are surface mount packages these days. Ball grid arrays, SOICs are where the pads are on the edge of the chip, but underneath the chip and don't stick out. All sorts of different ways this is done. So here's a project board. This happens to be a Microsimony Igloo. We're using a Xilinx part in our Nexus 4 board. And speaking of that, we may be a few boards short. There were some students that took a course this summer, and there's maybe 6 or so boards not turned back in yet. So I don't know. I just asked Justin to order another 15 boards. and he's going to try and get that done for another $3,000. And we'll see if we can't. Hopefully that way we'll have enough. So hopefully that can happen fairly quickly. So hopefully we'll be knocking those. But we may come up a board or two short. If that's the case, then we'll just have you can pair up with you can come to lab and pair up with somebody else and just work together, and that'll be fine for the first lab or two. But hopefully we'll get them in within a couple of weeks. Okay. Let's see. So here's the first homework. I think there's a homework folder on Blackboard. You should be able to pull this up. A couple of these things. So I do want you to, I want you to do these. Some of this may be confusing. You do need to read about this in the book. These UDPs, I put a lot more importance on this initially. For our purposes, we're not going to really get involved in UDPs. It stands for user-defined primitive. And it's kind of nice to know about these primitives a little bit, but for the most part, the hardware development environment takes care of this for you. You don't really need to know. And you're not going to create any user-defined primitives. So what this does, it allows you to make your own primitives. If you have, and this is typically more, it's somewhat more focused on simulation, but the synthesizer and the simulator use these primitives to implement your code. And typical primitive would be like an AND gate, a 2-input AND gate, a 3-input AND gate, a 4-input AND gate, an OR gate, an OR gate, an NOR gate, a NAND gate, an exclusive OR gate, an exclusive NOR gate, that sort of thing, a flip-flop. Although I'm not even sure there is a UDP for or a built-in primitive for that. But in any event, you can create your own, and there are certain rules to follow. So really, that's all I want you to write here: user-defined primitive. That's what a UDP is. In the port list for primitives is very defined. The output has to come first. The outputs have to come first, and then the inputs. But it's not true for your standard module. You can have inputs and outputs in whatever order you want in your list. But for a primitive, the outputs have to come first. So when you make a user-defined primitive, you have to follow that rule. And a module, how's a module different from a primitive? So a primitive pre-exists, it's in the machine, and you don't have to write it. You just have, in fact, in most cases, the synthesizer will just automatically substitute it where it fits into your code to implement your code. You can call them out specifically if you want as well, especially if you did user defines. How many times can you instantiate a module? Well, I'll let you figure that out. List all the logical operators, list all the bitwise operators. You should definitely pay attention to the difference between logical and bitwise, and explain the difference between logical and bitwise operators, explain the difference between the wire and register variables, at least give a few differences. Now, you won't know this off the top of your head today, that's fine. You've got a few days to work on it. If you don't have the book, you can probably just Google this on the internet and figure it out. In the book, it'll take a little digging, but you can figure it out as well. All right, that's the homework. Okay, here's what we're going to do. We're going to cover the bolded parts, and these are the rest of chapter 2 we'll cover as we go on in later lectures. So a typical design flow goes like this. Typically from, and maybe I'll put this over here. Let's see. Yeah, I'll do that. Typically we start with the requirements, and then so that's what the product needs to do. And then we have specifications for a device that will do that'll satisfy our requirements. And then we create the design using our hardware description language. Probably not schematic capture much anymore because devices are so complicated, you can't write a schematic. I think I've given you this example, but remember, if you think about the latest NVIDIA chips, there's one with 14 billion transistors on it. And I did the math for 4 billion transistors. The schematic would have to be 1 square mile if each transistor took up an inch in your schematic, a square inch. So 4 billion square inches was roughly close to 1 square mile. So that would be a piece of paper, 1 mile of length on each side, which is ridiculous. Where would you roll it out? How could anybody ever sit there and draw all those things? How could anybody ever get it right without making thousands of mistakes over that square mile? And then how could you use it? You couldn't, there's no way to use it. It's just not possible. So we don't use schematics anymore. We design these very complicated things with hardware description languages. And one of the ways we do that is we create modules. And then once we get the module created and we know it works, then we instantiate it and use it, but we never really look at the details of that module again. And a lot of times we'll have modules where we can change parameters so that we can maybe we can make them 4 bits wide, 8 bits wide, 16, 32, 64, whatever, and still use the same module. Okay, so then once we get the design entered, then we go through lots of simulations to make sure it's doing exactly what we want, that it's going to satisfy our timing requirements. And then we let the synthesizer turn it into an actual net list of gates and wires and everything that has to be connected. And then we'll simulate that net list so that that's pretty close to the hardware to make sure that now that it's been synthesized, that it still simulates correctly, because things can change. Timing constraints can cause hazards and other problems that we need to know about. And then once that's all done, now we go through the process of mapping, placement, and routing. Now, if we're going to use a new chip, we have pretty good control over that. If we're going to use an FPGA, then we don't usually have too much control. We can exercise a little bit of control, but often the synthesizer will do that for us, or the mapper, placer, and router will do it, which kind of part of the synthesizer too. And basically then we either come up with a bit file for our FPGA, or we come up with all the photomask required and steps needed for the foundry to make the integrated circuit. And there are probably a few other steps in there, like seeing how many we can fit on a given wafer, and figuring out what kind of bonding wires we're going to use and how they're going to package them. And there may be several different package choices. And in some cases, we may not bring out all the pins. In other cases, we may bring out all the pins, or even things that we might not bring out on other packages. Okay, so these steps all require lots of verification. So we go back, we iterate through these processes a number of times until we have a high confidence, especially if we're making a chip. If we're doing the FPGA, sometimes we'll go through this a little faster because you can just finally see, does it work? And you can do the final testing with your FPGA. If you have to reprogram it, it's no big loss. But once you develop all these photomasks and the steps in the foundry and you make a bunch of chips, you've invested a lot of money, and you don't want that to be, you want that to be right the first time if at all possible. And so that's why you do a lot of verification. You do a lot of sign-offs before you go to the next step. And that's where the supervisor sort of overseeing these things can, kind of honchos the engineers involved to make sure that that everything has really been looked at carefully. Okay, we, just like in logic design, sorry, got distracted there for a second. We talked about this in logic design, that there are levels of description. And so when we write our HDL code, we can describe it at the behavior level, and then eventually we can get down into the structural level. Sometimes we'll talk about behavioral, data flow, and structural, and then the physical realization of it. So when we talk about behavioral description, we're talking about the algorithm we're employing and how it's going to solve the problem we want to solve, how it's going to do what we want to do. But we're not specifying what kind of gates we're going to use. We may not even at this point be specifying whether we're making a chip or programming an FPGA. And we may not even be deciding how many bits wide these variables are going to be. But we just know we want to be able to add an A and a B and get a C. Okay. We probably aren't talking about what kind of adder we want. Ripple, carry look ahead, carry propagate, whatever. But we may have defined in our document, of course, in our requirements document, we're probably going to have some fairly clear descriptions of how this has to perform time-wise. Okay, so in any event, so we come up with stuff that looks like C equals A plus B. When we want to actually get down to the structural level, now we're gonna say, well, we're gonna use specific components. We're gonna have, maybe our adder is gonna be a carry look ahead adder. We're gonna implement it as much as we can with AND gates or lookup tables or whatever we're gonna do. And so this usually the design evolves from a fairly high level behavioral description to a structural description where we have to have specified some of the details. Now, as much as we can, we'd like to stay at this behavioral level because it's less work and we're rolling off most of the work onto the simulator, or the synthesizer and the simulators. So the synthesizer's going to do the heavy lifting, and as the years tick off, moving forward, the synthesizers are going to take on more and more of the structural decision making. So, for instance, when you write C equals A plus B in Verilog in the Vivado IDE, you don't have to go any further than that. You have to specify how many bits you're talking about, but what kind of adder is used, that's up to the synthesizer. It makes that decision on your behalf. And so if you wanted to go faster, if it winds up making a carry ripple adder instead of a carry propagate, then you may not get anything like the performance you want. Then you may have to go back and put some conditions on the synthesizer to make it do what you want it to do. So you might have to increase your degree of specification here. Your description may have to have some structural features to it to force the simulator to do what you want. The synthesizer to do what you want. Okay, so that's it's good as just a big picture concept to keep this in mind, that we're always that in the hardware description world, the synthesizer is doing a lot of work and making decisions, and you have to always remember, you may have to take steps to force it in certain ways. You are limited in how much you can do, and that's some of that high level stuff is kind of beyond the scope of this course, but you just should be aware of it. Okay, but not entirely. We'll go back and you'll see some of the labs where making certain decisions up here make a big difference in what the synthesizer actually does. Okay, so we write the code in hardware description language. The synthesizer turns it into gates. And what it really does, it comes up with this gate level net list. That's what the synthesizer outputs. It's a big net list. And then the router placer and let's see, forgot. Sorry, where was that? I want to try to get that right. That's right here. Yeah, mapping, placement, and routing. Okay. Okay, so that's what the net list does. And then the step after, once you get the net list, then we do the post synthesis simulation, and then we go through the mapping, plating and placing and routing. And that's important too. And the reason that's important is because there's some lines that you want to have some control over, particularly clock lines. And when the synthesizer, well, when the router routes your project on, say, an FPGA, it may very well, we have these big interconnect matrices going from slice to slice of the chip in the case of Xilinx, and it may route your signal very circuitously in such a way that it's there's actually, you know, something approaching a nanosecond or so timing changes, and so this can cause problems. And so sometimes you have to go mess with the routing, the mapping, routing, and placement step. We won't have to do that in our case because we're not doing anything that critical. But if you're really pushing the limits of speed, then you might have to. All right, so here's kind of this this is how we develop hardware. Obviously, performance and design time go up on this line, and density and degree of customization on this line. We talked about these programmable array logic, programmable logic array, programmable logic devices, which include PALs, PLAs, PLDs, but these days this stuff's kind of gone, and not too many off-the-shelf gates and in 74LS packages are being used, but we still use CPLDs, so they're out there. They're just much smaller than FPGAs, but they're not. They can be useful for a little bit of glue logic to connect two different systems together and that sort of thing. But mostly what we're doing are these field programmable gate arrays. These are big chips. Some of those chips have more than 1,200 pins on them. Just the chip we're using on our little board has 325 pins. So you look at the little chip in the middle of your Nexus 4 board, 325 connections. The next step after FPGAs is where we take an existing piece of silicon that's already been mostly manufactured, but there's one step left. And what's been manufactured is kind of like an FPGA. There's a whole bunch of gates or lookup tables or various things already pretty much created. And then all we're doing is creating the final layer to connect all these things together. And so this is kind of like a custom FPGA, if you will, but the real advantage, two big advantages. One, remember an FPGA uses a lot of its silicon real estate for its programming nature. Whereas if you do this programming with a mask, then you don't have that extra, you don't have maybe a teeny bit, but you don't have the significantly larger amounts of real estate used up by just the conferring the ability to make this a programmable device. So that makes the chip small, that makes these things maybe a little bit smaller. And the other thing that's really important is it gives you lots more control over the timing. So you get to really lay out all the clock lines exactly the way you want them, where you don't have that control with an FPGA. And then finally, the next step is just a full-blown brand new integrated circuit customized to your particular needs. So this mass programmable gate array, custom ASIC are kind of the chip level solutions. Whereas here you have an FPGA that's already been completely manufactured, and you go buy the chip, it's done, it's packaged, it's ready to go, and you just program it with a bit file. But here you're actually taking the final step in the foundry. So your time to market with an FPGA could be just a few days if you were really whipping it out. Whereas with the mass programmable gate array, you still got to get it scheduled in the foundry, and of course you're gonna make sure it's right, because as soon as they spend the money to do this, they're going to make a bunch of them for you, and if they're screwed up, it's going to cost you a pretty penny. So you don't want to do that. Whereas here you can, I mean, you still want to verify things because you could have a bug that would cause lots of problems. So you want to avoid that, obviously, but you can do a little bit of debugging work with the actual FPGA and program it with your sort of tentative code. And if it works great, then you can exercise it, make sure, double check it, make sure you've gotten any potential problems and bugs removed. But while you're developing it, you can be kind of, a little bit more casual with it and just try a whole bunch of different approaches. And that's one of the advantages of using an FPGA. It gives you that power. Once you start actually making silicon, then your cost, your penalty for mistakes goes through the roof. All right. And then in addition to this, now we have entire systems on chip, the SoC, where we not just have the integrated circuit part, but we build in maybe some analog front end stuff, some op amps, who knows what all, maybe even some chip level hardware to amplify analog signals, maybe to generate radio waves so we can modulate them and transmit stuff. So we do there's a lot of stuff that can get done that can be incorporated on the same piece of silicon with the silicon on chip or system on chip. Okay. So, we'll just say a word about VHDL here. This would stand for very high speed hardware description, very high speed integrated circuit. Let's see. Very high speed integrated circuit hardware description language. That's what the V is kind of an acrostic in there. Very high speed integrated circuit. So that's where the V in the VHDL comes from. So it's an acrostic within an acrostic. Okay, the VHDL came out of Ada. It was kind of created by DoD, and it has syntax that looks like Ada. You've probably never seen Ada. It's a little bit of an obscure language, but if you worked for Boeing or McDonnell Douglas or Lockheed or whatever, you would definitely have seen it. But not having worked for them and on DoD level weapon systems and aircraft, missiles and tanks and stuff, you wouldn't necessarily see this. But that's why it looks like Ada, because VHDL came out of that. And originally it was just set up to document the code. Then it was set up to simulate the code. And then finally, they figured out that they could actually make hardware with it and develop the synthesizers. Verilog came out about the same time. It was originally Gateway Design Automation, which was then purchased by Cadence. And then when they saw that VHDL was kind of gaining prominence, they made Verilog an open standard, and it became an IEEE standard. So both of them are IEEE standards now. And this had its syntactic roots in C. So Verilog looks a lot like C. Not exactly. And that can be in itself confusing, but it looks a lot like C. Okay. And then System C and System Verilog are just extensions to the Verilog language. And now in theory, you can develop some code in MATLAB, and then you may be able to output that as a System C code and have it maybe somewhat ready to go to create your hardware. I think this is still becoming mainstream and ready for prime time. It still has its problems, but Verilog is just a subset of this, so you'll be fine. Learning Verilog is still very important because it teaches you the things you can and can't do in System C and System Verilog as well. Okay. All right. So syntax for Verilog. So there are a bunch of reserved words which you can't use as identifiers. And then you have identifiers. These are module names, variable names, parameter names, a whole bunch of things like that. So all your various identifiers, here are the rules. They can include letters, numbers, and then two special characters, the underscore and the $sign. They must begin with a letter or an underscore. They are not allowed to start with a number or the dollar sign. And a lot of times the dollar sign will be reserved for system level stuff. But it is legal to be used. That's just convention, not a law you can't violate. Identifiers in Verilog are case sensitive. They're not in VHDL. And when you finish your statement, they end with a colon, unless of course they don't end with a colon, like some don't. So you have to kind of learn that. Okay, comments in Verilog are just like comments in C. You can do a double slash and then everything after that on the same line is treated as a comment, but the next line it starts over again. Or you can comment out a block of code with the slash star and then a bunch of stuff and star slash. Now, the only problem with the slash star star slash notation is that you can't nest within this block another slash star star slash. That'll screw it up, which is a big problem in my view. So that generally, I encourage you to make all your comments double slashes. And then if for some reason you want to comment out a big block of code, you can do the star slash slash star star slash. But nowadays, the integrated development environments let you highlight a block of code and then right click and select comment out, and it'll comment out the whole block you've highlighted with the slash slash on every line. And the nice thing about that is you can undo it the same way by highlighting the block you want to uncomment and right click and pick uncomment and then it'll pop the slash slash off of every line. So that's pretty cool. And it even works for comments, because if you already have slash slash, another slash slash is fine. And if you take off the extra slash slash, it won't take off the one that was really there to make it a comment. So that's a better way to approach. So I encourage you to avoid the slash star star slash nomenclature. Okay, so here's our description of a combinational circuit. We have a AND gate going into an OR gate. And so if we created a module of this, well, here we're going to have an assignment operator. So this is going to show up in your code. And the way you do this, you use the equal sign. And in this case, say that each gate has a propagation, a transport delay, an inertial delay of 5 nanoseconds. We'll talk about the difference between inertial delays and transport delays later on. I did mention it, I typically mention it in logic design, but it probably wasn't all that meaningful. So how would you take this simple circuit and write it? Okay, so you would write it like this, because they have this 5 nanosecond delay, assuming that you've specified your time increment as nanoseconds, you would do a sign #5. And now, because it's on this side of the equal sign, that is a inertial delay. If it's on the other side of the equal sign, it's a propagation delay. We'll talk about the difference later. So a sign #5, 5 nanosecond inertial delay, C equals A. And here we have the double ampersand. So you know from C, that's the logical AND. But because we're assuming these are bit variables, since there's no other comment to the contrary. So if these are single bits, the logical ANDing and the bitwise ANDing are exactly the same. But if they're vectors, if they're more than one bit, then logical ANDing and bitwise ANDing are not the same. So you do have to pay attention to this. I guess this is kind of convention, but I don't like it. I think you might as well just go ahead and use the bitwise operator, because what if you go back and redefine A and B as vectors, and then you forget to go change your logical operator to a bitwise operator? Might as well just have a bitwise operator there. They're different people have different theories about this, but I like to use the bitwise operators where you actually mean bitwise, even if they're single bits, and you could use the logical operators. And there is a sense in which you are doing a logical operation here, but it's also a bit operation. So I don't know. Anyway, I encourage you to use the single ampersand and the single vertical bar. Ampersand is ANDing, vertical bar is ORing. So here you have C equals A ANDed with B, and E equals C ANDed with D. Now, what happens if you write these in the other order? E equals C ANDed with D, and C equals A ANDed with B. Does that change what happens? If you do this first, well, if you do this first, does it use the new value of C here? That's a great question. And the answer is sort of. So the way these assignments work is whenever any of the variables on the right-hand side, so that would be A and B, C and D, change, then the statement executes. So if B changes, then C is going to update. That would make C change, potentially at least, and then that would cause C and D, C ORed with D, to execute and update E. And again, there is going to be this 5 nanosecond delay. So the answer is, it does not matter the order in which these appear or even where they appear in your program. If they appear in anywhere in your top level module, they will always be executed immediately as soon as the right-hand side changes. If it's in one of your submodules, that same thing will happen. And those results then will get back through wherever that module is instantiated in your top level module. Okay. So we call these concurrent statements, or sometimes we'll just call them assignment statements, because we use this keyword assign. Now, in Verilog, it's very permissive. So you don't really have to put assign. In fact, a lot of times we won't put assign there. We'll just leave it off. It's still fine. Everything works. So we do have some, the assignment up, this assign keyword is not required. So these concurrent statements, they're always ready to execute. They get evaluated anytime and every time a signal on the right-hand side changes. And this is the standard general assignment. You have an optional delay and the assign keyword, which is actually also optional, a delay, and then you have a signal name equal to some expression. The expression is evaluated. Then after the delay, it's assigned, the signal name assumes that new expression's value, which can only be 0 or 1. Well, for the most part. We do have disconnected high Z and some other things too, but generally that just 0 or 1. And here we go. Here's one with a delay. Here's one with no delay specified. All right. Now this is always this is a confusing slide because you can only do this in your. This is what we do to create a clock in our test benches. So we don't put this in our Verilog code. We put this in our test bench code to exercise our code. And so if you really synthesize this for real, you would have no idea the speed at which it would work, because you're not guaranteed these gate delays. And also it wouldn't be a perfect square wave. It'd be all screwed up. But in the simulator, it's a perfect square wave. And if you specify a gate delay of 10 nanoseconds for this particular inverter, you'll get a perfect 20 nanosecond square wave. And it'll look like that. So each half cycle is 10 nanoseconds. And you just say assign #10 clock equals inverse clock. This is the bitwise inverter. You could just as easily use the logic inverter here because it's a single bit. And if you put a different propagation delay, the clock would have a different period. Again, you can only use this in a test bench. Don't try and write this in your actual code because it just doesn't work. Fortunately, we have a clock on the Nexus 4 board that runs at 100 megahertz, and that clock is available to you if you through one of the pins. That's the clock input pin, and you just have to enable that in the constraint file, and then make sure your name matches the clock name in the constraint file, and then you can use that. And that's what we do. And we do use the clock a lot because Vivado and the Xilinx chips like you to have a clock, even though you might not need one if you're just doing a combinational device. But still, I recommend you use a clock pretty much for almost everything, because if you don't, sometimes you'll get a whole lot more convoluted hardware than if you have a clock. Okay, so here's 3 gates, and you have B. Excuse me. You have B, C, and A. A is going into every gate, and you have outputs D, E, and F. But each gate specifies a different propagation delay. So you would write this with different propagation delays, a sign and the propagation delays, and then the gate here, D equals A, and it with B, E equals the inverse of A, using the bitwise inverse. And here, so here using the logical and the logical OR. But again, with single bit variables, the logical and the bitwise have the same function. And again, remember, the synthesizer looks at this and creates a net list. So all this confusion completely goes away in the net list. Note, however, if A changes, then all these statements are going to execute because A is an input to all of them. So on the right-hand side, every single one. But the update times for D, E, and F are all going to be different based on these different propagation, these inertial propagation delays or inertial delays, whichever you want to call them. Okay, let's just say a little bit about multiple bit signals, and then I'll probably quit for today. So one of the real powerful features of Verilog is our variables can have more than 1 bit. They can be any number of bits. They can be 64 bits or 128 bits, but typically we'll make them 4 bits, 8 bits for stuff we do, maybe rarely more, but typically maybe 16. So this is kind of like a one-dimensional array. And you can also do 2-dimensional arrays. One of the things to keep in mind with 2-dimensional arrays is they cannot be passed in parameter lists. At least I think that may be an upcoming change in the next one of the next versions of Verilog coming out. So I have to double check to see if that's been changed. But last year it was, you couldn't put multi-dimensional arrays in a parameter list. So we'll see. I think they are going to change that eventually. So we have 2 designations for our signals for the most part. It's actually more complicated than that, but one designation is wire and the other designation is register. A wire is just what it sounds like. It has to be driven at one end and it connects to something on the other end. But a register is like a bank of flip-flops. If you have a 4-bit register, then you have 4 flip-flops, and they hold their value until you change it. And so once you put a value into the register, it preserves that value until it's changed. So this is a wire. It's a 4-bit vector. Notice how we do this. We have brackets, and then we put 3:0. So the reason we do this is because our higher order bit is our leftmost bit, our low order bit is our rightmost bit, the way we think about these things. And so we try and do our Verilog code similar to how we would think about these things. If we're, on the other hand, doing a list, an ordered list that starts at 0 and goes, say, to 10, then we would maybe go 0:10 or 9, 0:9. We always start with 0. Or end with 0. So if we're doing a 4-bit vector, it's going to be 3 to 0, or if it's an ordered list, it would be 0 to 3. And you can do it either way. But for most of our vectors where we're going to hold a 4-bit value, we want to put the higher order bit to the left. And then we also have one other strange convention, and that's the way we write constants. And we'll talk about this in a couple of lectures later on, because constants can be really, really confusing. But if you keep them simple, they're fine. The way this works is you put a number, which is the number of bits, not the number of digits, but the number of bits. And then you put a tick mark, apostrophe, and then you put the base. You're going to use binary, hex, or decimal. Yeah, I guess you can use decimal. And then you put all of the you put the numbers. In the case of if it's binary, then you can only put ones or zeros here. If it's hex, you could put, and if you had the 4 though is the number of bits. So say this was 4 tick H, you could only have 1 hex digit here because you've only got 4 bits worth. And if you had 8 tick hex, you could have 2 hex digits. And if you had 7 tick hex, you effectively get 7 digits. So if you specify 8 bits with your hex, the higher order bit's going to be thrown away. But anyway, that's where it starts to get really complicated when there's incomplete specifications, things left out, and you can also have signs. You can have don't cares. You can have a bunch of stuff here. So this can be really tricky. Okay. So this assign 4 tick B1100. It assigns the 4 bits. The higher order bit gets this one. The next bit gets this one, and the 2 low order bits get the 2 zeros, just like this: 1 to B3, 1 to B2, 0 to B1, and 0 to B0. So if you think about it, because we specified this 3 to 0, these numbers match up exactly. If we specified this 0 to 3, then that 1 would be the low order bit, and that's confusing because you don't think of it that way. So normally we write our vectors, the higher order bit colon to the low order bit. Okay. Let's see. I think I'm going to stop with that. So let me switch back. So we'll continue to pass out the boards in lab today. We'll see how we come out. We may have enough. I had a little trouble with the count, and I know there are a few students that had boards left over from their summer course that I didn't have included in the count. And then I have a few other boards. I have maybe 5 boards left in the office. So I may need to track down a couple of other boards, but I think I've tracked them all down except for the ones that weren't turned in from the summer course. And I think maybe there's 6 more of those. I don't know. But anyway, so hopefully we'll have enough boards, but if we don't, we're ordering some new ones. All right, let me stop and give you just a minute or 2 for questions. B3 would be 1. Yeah, where did you see? B3 is a 1.
No, Dr. Morton, if we did 8 apostrophe binary, and then I just put out an example number, would B3 now be 1, 1 instead of just 1?
Okay, let me see the example. No, B3 would be B3 would be a 1, but B2 would be a 0, and B0 would be a 1. It gets rid of the 4 higher order bits there are discarded.
Okay, thank you.
But that's what you have to be careful with. When we go over this, you'll see the rules are they get really skitsy. So you don't want to play games with the constants. You just want to make them all match up, and then you'll be good. And as soon as you start making things not match, Katie bar the door. The rules get very arcane. All right, any other question? Okay, you couldn't find anything under homework. Okay, let me look at that real quick. We'll just take a minute here. I couldn't hear you. You broke up completely.
We can pick up our boards at 2.
Yeah, 2 o'clock. We may not stay till. Of course, the labs are sort of scheduled 2 to 4:45, but we may not be there until 4:45. We'll probably only be there, and I may not come in at all because I need to take my wife to the hospital maybe. But anyway, we'll be there. Alex will be there from from 2 to 3 at least, 2 to 3:30, maybe 2 to 4. But don't come late. Come as early as you can. All right, let me see. What was the question on homework? It should be there, but maybe not. Let's see.
There's nothing in the homework folder.
Yeah, so let's see. Yeah, okay. Yeah, because they've all timed out. So I have to change all the due dates. I'll do that. Yeah, I've got a whole bunch of due dates to update on all 4 of my courses. I mean, it's just going to be hours of work to get all this stuff updated. It just takes forever to get it done. And we don't get to start in the middle of the summer because they don't make the courses available till later. All right, so yeah, I'll work on that. Let me make the first one available here. Let's see, change the edit. So it will be due, I forget when it's due, but we'll make it, oh, let's see, let me go back. So it was due 9:02, so it should be due 9:01. Yeah, okay, yeah, so that's when it's due. And then it's a week later, 9:09, 9:08, okay. All right, so now you should be able to see that. And I'll fix the other ones too. It'll take me a little bit. All right, I think that's it. Any other questions?
Hello?
Yeah.
Professor, can you hear me?
Yes.
Okay. So I remember yesterday we were talking about in microcomputer system, we're picking up the board from 10 to 3.
On Friday.
I also pick up, yeah, can I also pick up the board for this class from 10 to 3 on Friday?
Yeah, you probably could. Yeah, that's fine. You can do that. We'll be the same lab. Yeah.
Perfect. Thank you.
All right. All right. We'll talk to you later then.